Hello and welcome back to another episode of Math with Stone. Today we're going to be talking about AP Physics non-conservative forces, which is also known as a dissipative force, which is pretty much friction. All right, so to go back over the conservation of energy, it would indicate that the amount of energy that you start with will have to equal the amount of energy that you end with, but if there's friction involved, then you're missing some energy. So really, you have your potential energy in the beginning. If you add that with your kinetic energy in the beginning, if you were to typically, that would equal your potential energy in the final and your kinetic energy for the final. But if there's friction involved, that would mean that if you combine that to the original, or if you were to subtract it from the end, so to speak, then you would have your work done by your non-conservative added there, and that would be your friction. Okay, so notice how I'm saying work. It could be the energy, the kinetic energy of friction, but that kinetic energy of friction is essentially just known as the work done by friction. Okay, so with that in mind, we got our first example here. We got two, maybe three examples. A skier starts at rest from the top of a 20-degree incline and skis any straight line to the bottom of the slope, which is a distance of 400 meters. The distance of the slope is 400. If the kinetic coefficient of the skis and the snow is 0.2, calculate the skier's speed at the bottom. All right. So with that in mind, let's draw a picture here for us. We got 400 meters on the incline, and it is a 20-degree incline. All right. With that in mind, he is starting, I'm assuming it's a skier. They're starting up here and they are going woo down the slope. So if they're going down the slope, we want to know the actual speed at the bottom. So we need to figure out a few things here. We need to first figure out the height of this, because that will influence our initial gravitational potential energy. We will also need to figure out the coefficient of friction and how that's going to impact it. But let's start with our UI plus KI plus the work done by our non-conservatives, that would be friction. That will have to equal our UF plus our KF. Okay, so let's start with KI, because that, if the skier is starting at rest, it says it somewhere around here, skier starting at rest, that would mean that he had no kinetic energy in the beginning. The UI, that would be the height of this slope, and the height of this slope would be the opposite over hypotenuse with sine, and that would be h will equal sine of 20 times 400, essentially. Okay? You could also think of it as like the distance that they traveled. You could say sine 20 times d, or you could also think of h as sine of theta times the distance that you would have to travel on the actual slope. All right? So let's plug that in. It would be mg times the sine of theta times the distance that he would travel on the slope. We're using all variable form for right now. Plus the work done by friction. The work done by friction would be the kinetic coefficient of friction, technically negative m for the mu coefficient of friction, mg cosine of theta times the actual distance. And that is because the work done by friction is going to be cosine. If you're on the actual ramp, is cosine. It's a whole different video. It takes like 5 minutes to explain. We can link it in the description if we need to. Would equal the potential energy at the end. Well, the potential energy at the end, we're at the bottom, would be 0. So that's gone. Would equal 1/2 mv squared, and that would be our final velocity squared. So if we're solving for velocity, we want to find the velocity at the bottom, we would have to multiply all this by 2 and divide all that by m. But do notice that all of these have an m, so the m's would go away. Multiply everything by 2 and square root everything to be able to get our final answer. At this point, I think it would be messier to multiply everything by 2 and square root, so I'm just going to plug in everything at this point. So gravity we're going to be lazy and call 10, it's 9.8 meters per second. Sine of theta, which is 20, times our distance, which is 400. That's what we had here, sine 20 times 400. You could also write 400 times sine of 20, minus the coefficient of friction, which is 0.2, times gravity, we're being lazy, which is 10, cosine of 20 times 400 would equal 1/2 times velocity final squared. All right. And I've neglected to put in the units because I figured I would just run out of space with the camera. But this is 10 meters per second squared. This is 400 meters, so on and so forth. We need to type some stuff into the calculator. So what is all of that? 10 sine 20 times 400. 10. Let's see if I can put it all at one time on one part. 10 times sine of 20 times 400 minus 0.2 times 10 times cosine of 20 times 400 ends up being 616.32. So 616.326, and that would equal our 1/2 VF squared. So we need to multiply by 2, and then we need to square root. So multiply by 2, square root of the answer gives me a final velocity that is 35.1 meters per second. Bada bing. All right, next one. This next one, we're going to try and go through quickly. It is specifically AP Physics. If you're looking for like regular physics, I would go to like about 3 minutes into the future to find the one after that. This one is referring to only variables, and it is a safe that is kicked up an incline with an angle shown. It is has an initial speed of v. The incline has a coefficient of friction mu. What is the expression? Which of the following expressions is equal to the distance that the block slides before stopping? Okay. So we need to figure out the distance it would go before it stops. If it is stopping, that means that all of the kinetic energy will be turned into potential energy and completely gone. So let's see what that would look like. We got a separate sheet of paper here. We have the U initial plus the K initial plus our work done by non-conservatives will have to equal our U final plus our K final. We want the K final to equal 0. That block slides up the incline before stopping. So this part is 0. We know that it started at the bottom, so that is 0. So we got Ki plus the work by non-conservatives has to equal the last potential. Well, the distance that it will have traveled will be this distance here, which is on the horizon and like the diagonal part. So we need to utilize all of these to figure out what is going to be each one. For starters, we know that it is kicked with an initial velocity of v. So we're going to just write 1/2 mv squared there. We also know that the work done by friction would be the coefficient of friction times mg cosine theta, and that would equal the final potential energy, which is going to be, if we think about it, it would be like maybe it goes this high, maybe it goes this high. No matter what, it's going to be the opposite, and we need to relate it to the diagonal. So we need to figure out how this opposite relates to the diagonal. Well, it's currently sine theta is equal to opposite over diagonal. Okay, the diagonal is what we care about, so we need to solve for diagonal. That would be d is equal to sine theta on the bottom and the opposite on the top, and the opposite is the overall height. All right. Okay. So with that in mind, our potential energy is the height. If our potential energy is the height, our height is equal to the d times sine of theta. All right. So we are going to utilize this one, and we would have mg times height. Well, height is d times sine of theta. And there is our overall formula. What are we actually looking for? We're looking for d. If we're looking for d, we need to manipulate all this stuff around, and I'm going to kind of add this part over here so that we have this d, this cosine d here, and this d right there put together. So we would have 1/2 mv squared would equal m, coefficient of friction, mg cosine theta times d, plus mg d times sine of theta. And from here, I wonder if they all have a mass. They all have a mass. The mass will cancel. Do they all have a gravity? They don't cancel. From that, we're going to factor out a d from both of these terms. So if we do that, we'd have d on the outside. We'd have coefficient of friction times cosine of theta times gravity. Don't forget g. I almost did. Plus sine of theta would equal 1/2 v squared. We have d isolated. We can divide by this stuff, and we would have 1/2 v squared divided by the coefficient of friction, cosine of theta times gravity, plus sine of theta, and we would get our overall distance that we would be needing. And we would also understand why AP Physics is just sometimes annoying for no reason, because they like just manipulating formulas without actually doing the math. It feels like we did more math, though. All right, last one. This one I'm a little more excited about. It's cars, and they're going down an incline. I'm going to try and get through it quickly because we're already at the 12-minute mark in the video. So we have a 0.5 kilogram car. This car is going down a ramp. It wants to know the work done by friction from points A to B. We're going to assume that points A and B are here, and the car is just going down this ramp. All right? With that in mind, we will probably need to figure out maybe the angle. We'll find out if we do or don't. In the meantime, we need to figure out this distance, which is 10 from a 3, 4, 5 triangle. You can also use the Pythagorean theorem. 8 squared plus 6 squared would equal c squared, and you'd find out that that is 10 meters. All right, so let's do it. It has an initial. We got our ui plus ki minus the work done by non-conservatives, that's what we're actually solving for, will equal uf plus kf. All right, well, ui is how high we are in the air. It would be mgh, which would be I'm just going to write mgh, plus ki. This does have a ki because we actually started with something, which would be 1/2 mv squared, minus the work done by non-conservatives, will equal uf. At the bottom, it doesn't have a uf. Plus kf. Well, at the bottom, it will have a kf because it's still going at 14 meters per second. So this would be 1/2 mv squared. Now, if you turned your friction coefficient part into some stuff, then you could probably cancel out the masses. But it actually just is asking what is the work done by friction. So that would be if you were looking for the coefficient of friction or something else, but we just want to know the work done by friction. So let's plug in everything, or manipulate the equation first maybe. Let's add this part over and then subtract the 1/2 mv squared over. Final. This would be initial. So we would have mgh plus 1/2 mvi squared minus 1/2 mvf squared would equal the work done by non-conservatives. So let's plug in some stuff. We got mass, which is 0.5. Excuse me. 0.5 times gravity, 10 or 9.8 meters per second, times the height of 8, plus 1/2 mass, which is 0.5, times the VI. VI is 16 squared minus 1/2 the mass, 0.5, times the V final, which is 14 squared, would equal your work done by non-conservatives. I am being lazy and not writing in the units. I apologize in advance. If you do that, you get 0.5 times 10 times 8 plus 0.5 times 0.5 times 16 squared minus 0.5 times 0.5 times 14 squared. You get 55 as your amount of work done by friction, which I believe is in newtons. It's not Newton meters, is it? No. 55 newtons. I'm going to have to double check that because I am getting tired. Work done by non-conservative, which is the work done by friction. All right, that's going to do it for this one. Until next time, I will see everybody later. Bye.